Good morning children and welcome back to your chemistry class. In the previous video I had explained you about covalent bonding, right? So to proceed with, today I am going to explain you the failure of the octet rule. You already know what is your octet rule. So there are several stable molecules known to us in which the octet rule is violated, and therefore the heading that has been given to you is the failure of octet rule. That is, the atoms in these molecules, they have number of electrons in the valence shell either short of 8 electrons or they are more than octet or the 8 electrons, right? So today I am going to discuss with some of these examples where we find the failure of octet rule, right? So to begin with, let us take the first example of beryllium chloride structure, right? So this beryllium chloride structure, it is a stable molecule, remember. Beryllium is Be with valence electron 2, and it will combine with two molecules of chlorine, 1 2 3 4 5 6 7, and 1 2 3 4 5 6 7, right? So what it is going to show, both are non-metals, so definitely covalent bonding will be shown over here. So I can show it to you like this: beryllium, chlorine, 1 2 3 4 2 3 4 5 6. It can be shown like this. Now look at this structure. Here beryllium is attached with a single bond with the two chlorine atoms, right? So what did you see over here? This beryllium chloride, it forms a stable molecule. Beryllium atom, it forms two single covalent bonds with the two chlorine atoms, right? And it attains only 4 electrons in the outermost shell, right? Then next, let us come to another example. Boron fluoride. Boron atoms, they combine with 3 single covalent bonds with the fluorine atoms. Boron valence electrons are 3, right? Now this is going to combine with 3 fluorine atoms, so I'm not going to draw like this now. Now I'm going to take a little shortcut method to explain you, okay? 3 fluorine atoms, so 1 2 3 4 5 6 7, right? And what it is going to show you, it is showing you boron over here with 1 2 3 fluorine, fluorine and fluorine, okay? It is 1 2 3 4 5 6 7 8, then 1 2 3 4 5 6 7 8. Now see, fluorine 1 2 3 4 5 6 7 8 follows the octet rule, follows the octet rule and follows the octet rule. Now look at boron, 2 to 4 5 6. Does it follow the octet rule? No. It has less number of electrons than octet, but still it forms a stable compound forming 3 single covalent bonds with 3 fluorine atoms. I hope this is clear. So over here you can see boron, it attains how many electrons? 6 electrons in the outermost shell, not 8 electrons, and still it forms a stable compound. Here beryllium, it attained how many? 4 electrons in the outermost shell, and it is forming a stable compound over here. Let's take one more example of PCl5. Now phosphorus, the valence electrons are how many? 5, right? 1, 2, 3, 4, 5. And therefore it is going to combine with 5 chlorine atoms. 1, 2, 3, 4, 5, 6, 7. Okay. So let us look at the structure that it is going to form. This is phosphorus. 1, 2, 3, 4, 5. Chlorine. 1, 2, 3, 4, and 5. Okay, so first let us balance all the chlorines. So chlorine 7 and 1, 8. 7 and 1, 8. 7 and 1, 8. 7 and 1, 8. So all chlorine, they follow the octet rule. Now let us look at phosphorus. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. So what did I say? Sometimes the outermost shell attains less than 8 electrons, still it forms a stable compound. Sometimes it attains more than 8 electrons and still it follows a stable compound. So what kind of a bond are we going to see with the phosphorus over here? Phosphorus is combining with a single bond with the 5 chlorine atoms, right? Over here, what did we see? It forms 5 single covalent bonds with 5 chlorine atoms, right? And how many electrons does it attain in its outermost shell? 10 electrons, but still it is a stable compound. Now you are going to draw for SF6 molecule and IF7 molecule and see whether they follow the octet rule or they do not follow the octet rule. There is a failure of octet rule or there is no failure of octet rule to form a stable compound, right? Then one more example I'll give you, the formation of compounds that involve hydrogen. Right, like hydrogen, as you already know, has only 1 electron in the valence shell whose maximum capacity is how much? 2 is of 2 electrons only. Thus, it needs only 1 electron to complete its shell. So, is it following a octet rule? No, it is following a duplet rule. So, this is another one example of your failure of octet rule over here, right? Some more example like formation of compounds of noble gases, right? These noble gases, they have already complete octet in their valence shells and so they should not have the ability to form the compounds. But like xenon, krypton, they combine with the fluorine and they form compounds like XeF2 or even krypton fluoride is formed, or xenon tetrafluoride is formed, or even xenon hexafluoride are formed. So these all they go against the octet rule and form a stable compound. So I hope you have understood certain compounds which though are stable but they do not follow the octet rule, right? Now, what are some other limitations also or more drawbacks of octet rule? Like for example, these Lewis or these octet concept, they do not explain the nature of the forces that are operating between the atoms forming these covalent bonds, right? Then why different amount of energies are released during the formation of different molecules, that is not explained by this octet theory. Even the shape and the geometry of the molecules is not stable. It is not the same every time. So these are some of the drawbacks of the octet theory as well. Let us now talk about the polarity of covalent bond. Now you already know about the polarity of covalent bond. That is, I am here talking about polar covalent compounds and non-polar covalent compounds. So we already know that in all homonuclear diatomic molecules, what are homonuclear diatomic molecules? Homonuclear diatomic molecules. What are they? For example, hydrogen, chlorine, oxygen, right? So over here the electron pairs, right, or the pair of shared electrons, they are equal between the two atoms, right? This also means that the shared electrons are equally attracted to both the nuclei, and therefore equal amount of time near each nucleus is spent. As a result, what are these types of molecules also termed as? They are called as non-polar covalent compounds. Non-polar covalent compounds which are also neutral, right? But if we talk about some heteronuclear molecules, what are we talking about? Like we are talking about HCl, NH3 and so on, right? So, or even your you may say CH4 or CCl4. So over here we should understand the electronegativity difference is an important point over here. If there is slight electronegativity difference between the two different atoms, then it is going to show us a slight positive and a slight negative charges over itself. And if there is no electronegativity difference, then it is also going to be a non-polar covalent compound. So in case of methane and carbon tetrachloride, what do we see over here? That there is no electronegativity difference between carbon and hydrogen or carbon and chlorine over here. So they are again your non-polar covalent compounds. But if we talk about HCl and NH3, right? So we will see that H has a slight positive and chlorine has a slight negative charge present over them. Therefore, they are termed as what? They are termed as polar covalent compounds. So, you are already aware of all these things. Now, there are two kinds of notation how we can indicate a polar covalent compound. One is this way, or we can also show it like this, HCl and an arrow going like this. So this arrow always moves towards a more electronegative atom. So between hydrogen and chlorine, which one is more electronegative? Chlorine. So the arrow will move towards chlorine and we put a small dash over here, right? So this is another way of showing the polar compound and its polarity. So I hope this is very clear. So if there is no electronegativity difference, then they are non-polar covalent compounds. If there is slight electronegativity difference, then they are polar covalent compounds having slight positive and slight negative charges. But if electronegativity is large, then they become the ionic compounds, right? Now let us talk about dipole moment. What is a dipole moment? The polarity in a covalent bond, it can be measured by a physical quantity which is called as a dipole moment, and it is represented by mu, right? So how can we define what is a dipole moment? The dipole moment of a covalent bond in a polar molecule, it may be defined as the product of the magnitude of the charge that is present on either of the two atoms, right, and the distance by which the two atoms they are separated. This is called as dipole moment. So I write down the definition over here, which is represented by mu over here, right? So how can we define it? It is defined as the product of the magnitude of the charge present on either of the two atoms and the distance by which the two atoms are separated in the molecule, right? This is called as dipole, and this dipole moment mu, the dipole moment is equal to the charge into the, and it is a vector quantity. What did I say? It is a vector quantity, right? There are certain molecules which have a regular geometry. So the regular geometry means what? That the central atom, it has no lone pair, but it is attached to the identical atoms. Like for example, central atom has no lone pair and it is attached, what did I say? It is attached to the identical atoms. Then such molecules, they do not have dipole moment. Such molecules, they do not have dipole moment, or we say they have zero dipole moment, right? The molecules with irregular geometry, like for example HCl or NH3, where either there is a central atom which has a lone pair. You already know ammonia has a lone pair over it, right? Or maybe the atom is attached to another atom, or it is a heteronuclear molecule, right? Then it is said to have irregular geometry, and this kind of a molecule show dipole moment. Now when it is going to show dipole, when it is not going to show dipole, all that we are going to understand just now. So what did we understand over here? That the dipole moment concept is not applicable for homoatomic molecules where dipole moment is zero, right? But it is applicable to heteroatomic molecules where dipole moment is non-zero, right? So we should know over here that dipole moment depends upon what? It depends upon the charge and the distance. I hope this is very clear to you. So more the distance, the charge is the main dominating factor for a dipole moment of a molecule. Always remember, if more distance is there, the charge will be the main dominating factor for the dipole moment of a molecule. So charge basically depends on what? Your electronegativity difference. Now let us talk about the units of dipole moment. There are basically two units that we generally talk about. One is D, okay, which means what? It means Debye, right? It is given after a Dutch scientist, P. Debye. Then another one is ESU. What is this? This means what? Electrostatic system of units, right? And how are they related to one another? 1 Debye is equal to 10 to the minus 18 ESU, right? So these are the two units of the dipole moment. Now let us understand the question. Two equal and opposite charges, right, of plus this 1.5 6 into 10 to the minus 19 coulomb. They are separated by the distance is given to you, say 0.15 nanometer, right? So you have to find out the dipole moment in coulomb meters and also in debye. So what is the dipole moment equal to? Charge into distance. So let's find out what is the charge. 1.6 into 10 to the minus 19, right? Coulomb into what is the distance given to you? 0.15, but it is in nanometers. You have to convert it into meters. So what are you going to do? 0.15 into 10 to the minus 9 meters. When you calculate this, 1.6 into 0.15 is going to give you as 2.40 into 10 to the minus 29 coulomb meters, right? Now we should be knowing that 1D is equal to how much coulomb meters? It is 3.335 into 10 to the power minus 30 coulomb meters. Therefore, now if you find out the dipole moment, it is 2.40 into 10 to the power minus 29 upon 3.335 into 10 to the power minus 30. So this is going to give you approximately 7.196 debye, right? So this is one way to calculate your dipole moment. Now further, let us understand that greater, again I am repeating, greater the difference in electronegativities of the bonded atoms, greater will be the dipole moment. Hence, greater will be the polarity of the bond also. When the difference in the electronegativity is 0, then a non-polar covalent bond is formed. I hope this much you will remember. Now let us understand these dipole moment of polyatomic molecules. I am going to explain you with certain examples over here. So before I start with the examples, you should know that the dipole moment of a polyatomic molecule, it is always obtained by considering the dipole moment of each bond, right? So the directions of the bond dipoles, they decide the resultant dipole moment of the molecule. If equal dipoles are directed in opposite directions and the bond angle is 180 degrees, that means it is forming a linear structure, then the dipole moment of the molecule will always be 0, though each bond has a dipole moment, right? For example, let's talk about the dipole moment of beryllium fluoride, which is the dipole moment over here is 0. Now why is it 0? Now look over here, that beryllium F and F, right? So in this molecule, each beryllium and fluorine bond, it is polar. Why? Because F is more electronegative than beryllium. So this means this is electronegative, this is electronegative, this will be electropositive, and this will be electropositive this side, isn't it? So the direction, what we are going to show, it will move towards more electronegative atom, right? Thus, what do we see over here? Since the two equal dipole, they point in opposite directions, hence they cancel each other, and thus the molecule of your beryllium fluoride has no net dipole moment, or we say the dipole moment is 0. I hope this is clear to you. Okay, then we take another example of CO2. Over here also we will see the dipole moment will be 0. Now how are we going to see this? Carbon, it combines with double bond O, right? So the dipole moments of carbon and double bond O, they are equal but they are directed in opposite directions. Therefore, the vector sum or the net dipole moment becomes 0. Why? Because this is electronegative, this is electronegative, this is positive, this is positive. So this is going to move towards more electronegative opposite direction. Therefore, net dipole moment is 0. Let's take another example of water. The dipole moment is not equal to 0 over here. Why? Because water does not show 180 degrees, right? But it shows a bent polar molecule. It is a bent polar molecule, right? So it has a dipole moment. So over here, if I draw it, look at the structures of water. Hydrogen, hydrogen, and they combine with oxygen, which also has a lone pair, and this is formed at what degrees? 104.5 degrees. Clear? Now look at the charges present on it. I'll draw it separately to show it to you clearly. This is electropositive, this is electropositive, this is electronegative, this side electronegative, right? So from positive to negative, from positive to negative. Clear? So in water, the oxygen atom is more electronegative than hydrogen. Therefore, what have I shown you? The oxygen atom attracts the bond pair of electrons, right? Towards itself. In this way, a negative charge develops on oxygen atom and a positive charge develops where? At hydrogen atom. Thus, the hydrogen oxygen or oxygen hydrogen, it forms a bent structure, and this forms the dipole moment this side, and therefore we see what? The resultant dipole moment is not equal to 0. Followed? Next, if I compare the dipole moment of NH3 and that of NF3. Which one is greater? Dipole moment of NH3 is greater than that of dipole moment of NF3. Now why and how we can explain this? So firstly, I am going to draw the structure and then I am going to talk about and explain you the whole thing. So let's draw the structure of ammonia. N, H, 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 and here is the lone pair. Clear? Let's draw for NF3. N, F, 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 and it also has a lone pair, right? Now over here, look, this hydrogen is more electropositive than nitrogen, so they all move towards nitrogen, right? And the direction of the movement due to the lone pair of electrons on the atom moves upward, right? So over here we find that there is dipole moment, means there is a resultant dipole moment, and which is not equal to 0 over here, right? So what did we observe over here? That in ammonia the nitrogen is more electronegative than hydrogen, and therefore the NH bonds, they move more towards nitrogen. Thus the bond moment of each NH and that of your lone pair, they are all moving towards the central nitrogen atom point, right? And also in the same direction. Thus, what do we see? That ammonia has the dipole moment. Now we have to see the dipole moment. Is it found over here? And then we will compare which one is larger, right? So over here, nitrogen and fluorine. Now fluorine is more electronegative than nitrogen, right? So what is happening over here? They will move outwards and this goes up, right? So over here, what is happening? In NF3, fluorine is more electronegative than nitrogen. Therefore, your NF bond moment, it is directed towards your fluorine and which is away from nitrogen. We also see that dipole moments, they are moving away from each other, right? So what do we see? The moment due to the lone pair of electron, it is also directed away from this one. It is directed away from the nitrogen atom. Therefore, we can say that this NF3, the bond moment of each NF bond and that of the lone pair on the central atom, they are in the opposite direction. For NF, they are in the opposite direction, and NF with the lone pair is also in the opposite direction, right? So this also has a dipole moment. But now let us compare these two structures. So here you will find what? They are all coming to the center, and then this is moving away from it, right? Whereas over here, all these NF, the bond moments, they are moving away from each other, and even the lone pair is moving away from each other, right? So we can say that ammonia has dipole moment greater than the dipole moment of NF3. I hope this is clear to you. Now let us understand certain applications of dipole moment, okay? Applications of dipole moments. So decide the polarity of the molecule. I hope till now you have understood. They decide the polarity of the molecule, that is molecules whether they have zero dipole moment or they do not have zero dipole moment, whether they are polar or whether they are non-polar in nature, that is decided by the dipole moments. Then secondly, they help to determine the percentage ionic character, okay? They help to determine the percentage ionic character. So over here you note down the formula for it. That is, it is always equal to experimental value of the dipole moment upon the theoretical value of the dipole moment into 100, right? This is the formula to determine the percentage ionic character, right? Then they also help to determine the geometry of the molecule. Determines the geometry of the molecules. For example, like just now we had studied carbon dioxide forms a linear structure where dipole moment is 0. Then just now you studied about water, right? It is not a linear molecule, it forms a bent structure, so it shows a dipole moment. In ammonia also you saw that it forms a pyramidal structure and it forms a dipole moment. So it also determines the geometry of the molecules. Then fourth point, it also helps to determine the orientation in the benzene ring. Determines orientation in the benzene rings. What do we mean by orientation? Dipole moment is very useful to ascertain the orientation in the benzene rings, right? That is, greater the dipole moment, greater will be the asymmetry. That is, ortho will have more dipole moment than the meta, than the para, right? Over here, ortho will have more dipole moment than meta, and the least dipole moment over here will be that of para. And lastly, it also helps to understand the bond moment, that is the contribution of the individual bond in the dipole moment of these polyatomic molecules. It is called as the bond moment, right? And it is, as I had told you, it is measured dB or in ESU. So that's all for today. Next chemistry period I shall be picking up your Fazan's rule and also will complete your coordinate bonding. Thank you.